when we are determining the value of an integral, or we are integrating, what we are doing is changing from a function that is known to a different function that gives us different types of information. So typically we would do this if we know a function maybe for velocity and we are looking to change that to a function of position, or we know an acceleration function, something that depends on time, and we're going to change that to a velocity function. So the example here is already sort of set up for us. We'll talk in a second how we would set that up ourselves, but let's just remember the process of integrating. So what we would do here is, instead of writing negative 15 times t to the fourth, we would increase the exponent by 1. So we go up to a t to the fifth power, but at the same time we would change the coefficient. We would divide that coefficient by that new exponent. And we'll simplify this in just a second here. Let's do the same thing for the next term. So we have 8t. So we will increase this exponent. So if I just see a t, that's t to the 1. So it goes up to t to the 2. And again, I divide by that new exponent. Let's go ahead and simplify this a little bit. So negative 15 over 5 would be negative 3. So negative 3, 5, t to the 5. And then 8 over 2 is 4. Now, you don't necessarily have to write this step here where I kind of wrote out those fractions. If you can do that math in your head, that's fine. So this would be just about our ending answer, but it's possible that there is a constant term. So remember that when you take a derivative, the constant term disappears as you move to the next function. So if you go backwards and you integrate, there's a possibility that there is a constant term in this function that we're creating. So in a math class, they would typically just use c for constant that they would add to the end here. We'll talk about that in just a second. But that would give us kind of a general statement of this new function that's being created. All right, but again, we're in a physics class, so there's a purpose to our process here. We might be given or know some sort of expression for velocity, and we're going to determine an expression for the position function instead. Okay, so that's why we would be doing this. So we could set up an equation, or a statement here, that says my function x, or you could write x of t, will equal the integral of this velocity function. Okay, so that's the general idea. So we are integrating 8t to the third power plus 6t minus 5. Okay, and now we'll go through and do this process up above. Again, we'll raise the exponent. So I'm going to lose this integral. Okay, so this symbol here is when it's the old expression, and now I'm creating this new expression, and so I drop that integral symbol. So I change this to 8t. I raise my exponent, increase the exponent to 4, divide by that new exponent. Okay, this is 6t. t is t to the 1, so it goes to t to the 2. All right, and then this one doesn't seem to have any sort of t in there, so it's kind of like it's like a t to the 0. Okay, so when you raise it, it goes to t to the 1, or a t sort of is grabbed as you do this process of integrating. So this becomes negative 5t. And again, there would be a constant added to this. But the constant that we would be adding, you could call it c, but since we know that we are determining an expression for x of t, this constant means something. It's the value of this function when the time is 0. You can imagine putting 0 in for all the t's and how x would equal just the constant value. And so really the best answer that really gets at what we have determined from a physics point of view is to go through and simplify all these fractions and then to call my constant x sub 0. Okay, to call my constant the initial position of the object. All right, so there's also something called a definite integral. Okay, and a definite integral would be used to determine the actual change in some sort of quantity. So again, if this 6t squared minus t, if this actually told us what the velocity was, if that was my velocity function, if I integrate, it gets me a position function. But if I compare the starting and the ending positions, that doesn't really look very good. Let me try again. If I compare the starting and the ending positions of something, this tells me the change in the position or the displacement. So that's kind of the idea that I'm going to be using as we look at this here. So let's go ahead and evaluate the integral, and then we'll do the definite part of it. Okay, so again, my general expression that I'm going to get here, I'm going to raise my exponent to 3 and then divide by that new exponent. This one doesn't have a coefficient in front, so it's just t to the second power divided by 2. Okay, so my general expression is 2t cubed minus t squared over 2. All right, so what I'm going to do now, again, there would be a constant added to this, but you're going to see in a second why I don't really need to worry about that constant. I'm going to put it in green, but we're going to notice how when I do a definite integral, I don't really need to include it here. So what we're going to do is we're going to evaluate this expression at the 2 points given here, 2 and 3. Okay, and the way that this is often written is we just draw a long line, and we say we're going from t equals 2 to 3. So I'm going to put the later time in first. Okay, so I'm going to put in 3 for my time. Okay. And again, we're going to see how this doesn't matter what this value is here in a second. All right, so this would be the value of this expression at 3, and then I would do the same thing, but I would put in 2 for my time. Okay, and then again there would be a plus c here officially. Okay, and then what I'm going to do is I'm going to subtract these two expressions. Okay, so I'm using this idea that I'm really finding the change in this expression between these two moments in time. And so I'm going to take this amount and I'm going to subtract this amount. But when I do that, this has a c in it and I'm subtracting a c. So these constants always drop out. They always subtract out. And so when we do this process, we generally don't even include the c at this step, because eventually with a definite integral, that constant disappears. So why bother putting it in there and making my life more complex here? All right, so at this point we would just grab a calculator and go through and do this. So I don't have a calculator with me, but so hopefully I get this right. But 54 minus 4.5. No, this is supposed to, yeah, 4.5 minus, and then this would be 8 times 2, 16. I apologize for not having a calculator with me. Hopefully I'm doing this right. So, you know, you're just going to, whatever it takes to find the answer, I certainly would just plug this into a calculator. But this is going to be 41.5 would be my answer. And now again, what does this mean? What does this tell us from a physics point of view? Well, if this function here, if this had been a velocity function, when we integrated this, when we found this definite integral, we would be finding the change in x. When you integrate velocity, you get position information. And so this value that I just found would have been how far the object moved during this 1 second of motion, from t equals 2 seconds to t equals 3 seconds.